In this video, we will explore one of the common simplified methods for the design of mechanical clamps, and then we will prepare an Excel sheet for the calculations, and this should be shared as part 2 of this video in the next video. In the description of this video in YouTube, we will add a link to download this presentation as a PDF format if you are interested. Mechanical clamp consists of two split fittings mechanically joined together to seal off or reinforce a component, and the annular space between these two parts and the component inside it can be whether left empty, or it can be filled with some kind of lining, epoxy, or sealant, or any refractory material. The clamp can be categorized as whether to be non-structural, which is designed to contain a leak, or structural, designed to reinforce and hold together a damaged component. The main components of the mechanical clamp is the main shell, and that's why during the mechanical design we will go one by one step for each of these components: the design of the main shell thickness, design of end flat plate thickness, and design of lug thickness, and specifying the number and size of bolts. In this video, we will explore only the non-structural clamp and non-gasketed metal-to-metal contact with the sealant injection applied, and assuming that there is stable and uniform operating conditions. Any of those assumptions, if it's not applied or is not achieved, means you might need some other more detailed design method, and you might also explore the application of finite element analysis. The first part number 1, the main shell thickness. Main shell thickness is a cylindrical part. Simply, we can follow the rules of ASME section 8 division 1 UG 27, where we can apply the internal pressure to be like what we can see in equation 1. And here the pressure to be applied should be the maximum of whether the design pressure of the line, because in case the internal line leak will fill the gap between the leak line and the clamp. So in this case, under some certain condition, it might reach to the design condition of the line. So that's one factor, the design condition of the line. And the other factor, if in case like what we have assumed here, you will apply a sealant injection. The sealant injection usually applied with a pressure a little bit higher compared to the operating pressure, so that it can resist the leak during the installation of the clamp, and it can stop the leak. And usually we are applying 10% over the operating pressure. So the design pressure to be used for the shell of the clamp to be the maximum of whether the sealant injection or the design pressure of the line. And part number 2, the flat end plate. The flat end plate can be designed as per the rules of ASME section 8 division 1 UG 34, the equation which we can see here identified as equation 2, where we'll use the allowable stresses from section 2 part D for the plate material at the design temperature, and apply the design condition, design pressure, which we also applied in the previous part for the main cylindrical shell. Now for the lug thickness. For the lug thickness, we will try to apply the equation from Appendix Y in Section 8 Division 1. And the Appendix Y equation is applied for the circular flange. This is the one which we can see in the top here as equation 3. So we will see how we can derive this equation so that we can apply it also for the rectangular lug. First, the section modulus. Section modulus section modulus is a geometric property for a given cross section used in the design of beams or members, and the section modulus is defined as the ratio of second moment of area and the distance from the neutral axis. So if we are need the section modulus, the y and the distance here will be the maximum distance, and the moment of inertia, the moment of inertia for the lug, which is the rectangular shape, we can apply simply the standard moment of inertia equation, as we can see L, the total length, t cube over 12, and the y maximum here means from the neutral axis to the maximum distance means thickness over 2. Y maximum will be t over 2. Now substituting the value of I and the value of y maximum in the equation of the section modulus, it will end up as what we can see and simplify to be LT by t squared over 6. Now for the equation of the moment of inertia to the sorry, the bending moment to the area moment of inertia equal to the stresses over the distance, and if we are talking about the maximum bending moment, so it will be sigma maximum over y maximum. Now the m from this equation we can simply see m is equal to sigma maximum I over y, and I over y is the section modulus, so we can substitute the section modulus from this equation, so m will be L t square over 6 sigma maximum. From this equation we can get the t equal to the square root of 6m over L t sigma maximum, which is 2.45 sigma m LT over sigma maximum. Now just compare this one for the circular flange, the shape of appendix Y in ASME section 8 division 1. L is here the length will be the circumferential length at the pole circle diameter of the bolt, excluding the bolt hole itself because it's not somehow supporting in the beam itself, as if you consider it as a beam. So L here will be by C minus N, which is the number of bolts, multiplied by D, which is the hole diameter. So L will be by C minus ND. And the sigma maximum here, the sigma maximum from the perspective of mechanical design, we will consider it like the allowable stress. So substituting here the L in this equation by what we have got here, and the sigma maximum by the stresses, we will find that this equation can be expressed like 2.45 square root m over pi c minus nd multiplied by s, which is the same equation which you got from appendix Y. So now applying the same concept to the non-circular flange to get the lug required thickness, the distance here will be LT minus ND by the same concept, and because it is have two lugs from both directions, so this will be multiplied by 2. So substituting again the L in our equation, in this equation, and the sigma maximum by the allowable stress means for the non-circular flange for this lug, the thickness will be 2.45 square root m over 2 multiplied by LT minus ND multiplied by the allowable stresses of the lug material at the design temperature from section 2 part D. And in this case, just in some design, the lug will be might have a little bit irregular shape. So all the point here, like you need to calculate L all around. Maybe it will be not symmetrically from both sides. So you need to sum the L from this side and the L from the other side all around, and this will be substituted as L in this equation. So you can use now this equation for the calculation of the thickness of the. Now for the minimum required bolt load, here the hydrostatic force which try to separate the two parts of the clamp will apply on the area inside the clamp, like what we can see here. So area will be L multiplied by ID. So this is the area. Somehow there is another component inside, but you can conserve the part which is there, but you can conservatively use the full area here for the calculation. So the hydrostatic force acting on the area, ID, the internal diameter of the clamp, multiplied by the length of the clamp, and then the hydrostatic force will be the area multiplied by the design pressure, and should be the same design pressure as identified, the maximum of whether the line design pressure or the sealant injection pressure. Now the required bolt load shall not be less than the F which we calculated here, and it's better to add also some factor of safety, maybe 10% or so. Don't forget that we are applying some simplified method, so consideration of factors of safety is important. Now the allowable bolt load to be calculated, which is the A of the bolt, the area of the bolt for the root area of the bolt, multiplied by the allowable stress of the bolt at the design temperature and the number of the bolt. Now the allowable bolt load shall be higher than the required bolt load which we calculated from this value. By that we can define the number of bolts and the size of the bolts, and the area of the bolt. You can use the root area of the bolt from ASME BCC1 table H1M to get the area of the bolt required in the calculation. Now to get the applied moment in the equation 3, which in the previous slide, we can use ASME boiler and pressure vessel code appendix 2x for the reference for the HD value, which is the arm of the moment to be applied. For the loose life flange, it is C minus B over 2, where C is the bolt circle diameter and D is the ID of the flange. So similarly, we can apply the same here. So the moment arm will be C minus the ID of the clamp. Put the same in the equation 3, or equation 4 from the previous slide. You can get the thickness equation, which you can use here for the required lug thickness. Now we'll put the same procedure which we followed in the previous slides in a simplified flow chart. So first you need to select the clamp material, bolt material, and get allowable stress at both ambient and design temperature from section 2 part D, and it is highly recommended to use the clamp material matching the line material. Estimate the clamp dimensions, bolt size, and numbers, and in this case it is very important to check the actual dimensions of the leak pipe at site. Don't just use the nominal dimensions from the standards. You have to verify the actual dimensions at site. You have to do an inspection to see the extent of the clamp to be applied. Now determine the sealant injection pressure. As an approximation, usually it's applied like 10% over the operating pressure of the line. Now calculate the thickness of the clamp main shell thickness using ASME section 8 division 1 UG27, using the maximum of the design pressure of the line and the injection pressure as we said. Then calculate the thickness of the end plate using UG34 equation. Then calculate the total hydrostatic force using the area inside the clamp and the design pressure. Then calculate the required bolt load and calculate the available bolt load using the area of the bolt, the root area of the bolt from the table from ASME BCC1. If the required bolt load is still not is less than the available bolt load, means you have to run again and increase maybe the size or the number of the bolt loads until achieving like the available bolt load should be higher than the required bolt load. Then to calculate the lug thickness, and by that you have into the recommend or required clamp dimension. Here some general notes. When using the use the clamp material matching the line material, you need to check the line itself under the effect of external pressure applied by sealant injection. So you have to do an inspection for the line, get the actual thickness and the extent of the thickness loss, and to see by the design rules of ASME section 8 division 1. And we have one Excel sheet and video from a previous video. You can use it as a guide for the external pressure calculation. And the MSDS for the sealant component to be checked, and it should be compatible with the media and with the service and with the material also. It is recommended also to use the corrosion allowance similar to the applied for the main line, and to check the line support at site whether some adjustment might be required for some spring hanger or spring supports, or some additional supports might be required to take the load from the weight of the clamp. Check the axial thickness of the leak line before the application, and in case a leak resulted from crack, it is very critical exercise. Some special cautions shall be considered, and as a guidance you might refer to ASME PCC2 article 306. There is some guidance for the clamping required in case there is a crack. At high temperature application, just take sure that you have selected the proper bolt material. The normal B7 bolts has very low allowable stress at high temperature. You might need to apply B16 or B8 bolt. And from the ASME PCC1, while applying the target bolt stress for the tightening of the clamp, you need to consider the requirements and recommendation as in BCC1 as mentioned in these 2 points for the lower and maximum limit. Sometimes for more complex clamp or structural clamp, you might need to have a finite element analysis to be applied. Those are the references and recommended readings which you might refer to for more details. And would like to thank you for following this video, and there is a link on the description of the video to download this material in PDF format, and we will follow with part 2 of this video for an Excel sheet for the calculation following this procedure. Thank you.